Okay.
So the total session is at 1 hour, right? Including
Yes, sir.
Q&A.
Yes, sir.
I'm actually comfortable with both. I mean,
Okay, sir.
if any participants want to ask questions at that particular time, I'm happy with that as
Okay, sir. Okay, sir. If
well.
any question comes, then we will ask you.
Sure, sure, sure.
Okay,
Yeah,
sir. Thank you, sir. Thank you so much, sir, for joining us.
yeah, no problem.
Please be with us.
Sure.
Hello, sir. So it's 7 p.m. now. Should we start, sir, with information?
Yeah, sure. Yeah, let's go ahead.
Yes, sir. Okay, sir. So welcome you all. Welcome to all of the participants. Hope you all are safe and well. So today IEEE Computer Society Student Branch Chapter welcoming you in the webinar on self-supervised learning for histopathology image analysis. So today we have Mr. Dwarikanath Mahapatra with us, and we would like to just give a short introduction of him. So Mr. Dwarikanath Mahapatra is a senior research scientist at the Inception Institute of Artificial Intelligence, Abu Dhabi, UAE. His current research focus is on applying artificial intelligence and deep learning to challenging problems in computer vision and medical image analysis. He obtained his Ph.D. from NUS Singapore and worked as a postdoctoral research fellow at ETH Zurich. Thereafter, he worked as a research scientist at IBM Research Melbourne. He has co-authored more than 80 papers in the area of medical image analysis. So welcome you all. Welcome to our speaker. Thank you, sir, for joining us today. And I would like to request all of the participants to ask your questions in the chat box. And for those people who are not able to use the chat box, who are the first, who have been the first time in the Microsoft Teams, please use the YouTube and Facebook channel, because we are happy to announce that we are also live in our YouTube channel and Facebook page. So go there and ask your question. Our team constantly monitoring all of the channels. Your question will be asked. Don't worry. And one attendance sheet will be circulated during the session. So you can, as our speaker has said, that he is comfortable with taking question in between of the session also. So you can ask any question in the chat box. We will ask the question to speaker. Okay, so thank you, sir. Over to you. Now you can start your speech.
Okay, thank you. Thank you, Sricheta. Good evening, everyone. And first of all, a big thank you to the student chapter of IEEE Computer Society at IIT Kharagpur for inviting me for this seminar. I really consider it a privilege. So without much delay, I will start my presentation. So my presentation is titled Self-Supervised Learning for Medical Image Analysis. I will lay particular emphasis on histopathology images because that's what I work on primarily. So a bit of my background. So I did my bachelor's in electrical engineering from NIT Rourkela, which is not very far from IIT Kharagpur. In fact, I actually spent 3 months under Professor Aurobindo Rautray during my summer internship. From May to July 2005, I worked on a project for emotion classification. Then I did my PhD from NUS and spent 4 years as a postdoc at ETH Zurich. Then again 4 years as a research scientist at IBM Research Australia. And my interests are in deep learning, medical image analysis, and computer vision in general. So I have divided my talk into different sections. So I would suggest that if you have questions at the end of each section, I'll wait for some time, and if you have questions, you can ask after each session. So what exactly is self-supervised learning? Like a short intro on that. So we all know about supervised deep learning, which works very well when we have lots of data, and there are a lot of applications that have been using it, including commonly on YouTube, Facebook, Instagram, and it involves different content understanding, filtering, tracking, classification, face detection, all these items. But what about the situation when we don't have the lots of annotated data? So then, so self-supervised learning, I'm pretty sure many of you are familiar with that. But just to explain it from a very high level or a simplistic perspective, it's like filling in the blanks. So if you have so you have some data annotated, but you kind of pretend that there is like part of the input is missing, and you predict the input or the labels of that masked part from the other part, which you can see. So it's like predicting, I mean, in different ways, predicting future from the past and all. But of course, in all this, we do know that there is some way to generate the labels, either by some artificial manipulations or masking certain parts of the input or image. So the first part of my, or the first topic of my talk will be on informative sample selection. So just to give you a brief heads up is some sections I'll go in detail because those works have already been published, and some other sections I'll go on a very high level because the works are still under review. So I mean there are many co-authors and we don't have permission to share everything. So the first part is about informative sample selection. So anyone who has worked on medical images, or for that matter medical data, knows that lack of annotated data is very common in images because it requires a lot of time from clinicians. And since their time is precious, we want to make optimal use of clinicians' time and effort. So in that perspective, sample selection is actually essential to achieve optimum system performance with minimal input. So that means whatever input the experts are giving, we should make optimal use of that. So what we have done is we have used deep features from saliency maps, and then we have combined them with self-supervised learning for selecting these informative samples. And we demonstrated using classification and segmentation experiments. So to look at how relevant are saliency maps. So this problem is actually, this informative sample selection is a core part of active learning models, where you have to select the most informative sample, then give it for annotation to the expert. So if you look at this image, and so first we show, so there are two images, chest X-ray images. So top row is like the highly informative image, bottom row is the less informative image as selected by clinicians. So then we have these two types of saliency maps. So in the column B, we have from a method called deep Taylor decomposition, and then column D is something called Grad, which is it is about uncertainty, using uncertainty. And we look at the distributions of the saliency values of the high informative and low informative image, and we find there is a very clear separation. So actually that is the kind of the basis on which we assume that we can use saliency maps also for active sample selection. So we design a method that we term as IDEAL, which is actually short for interpretability driven sample selection framework. So what happens in this IDEAL framework is that we have some samples coming in, let's say at test time or the active learning cycle. We have a trained classifier. We classify that images, and we also using that backpropagation and other saliency map generators. We generate a set of saliency maps for the batch of images coming in. Then we have this ideal scoring module, which takes the saliency maps and outputs a informativeness score or an ideal scoring for that. And then we rank all the different samples based on their informativeness. Now in this framework, it would be easy to rank which is highly informative, which is least informative, if we had pre-labels of those images that are coming in. But in reality, we do not know which is highly informative and which is not highly informative. So that is where the self-supervised learning comes into play, and I'll explain that subsequently. So first, just a brief overview on some of the components. The classification model, it can be any common classification model. Like we use 3 different models, DenseNet 121, ResNet 50, and VG16, and found DenseNet gives the best performance, which is not surprising because it has these connections, reusable connections, and it transmits the information from each stage to all the previous stages. And then for the saliency map generator, we also investigated 3 different approaches, so Deep Taylor, GradCam, and LRP. And we found the Deep Taylor gives the best results for this particular application. We would also show that why we use Deep Taylor over GradCam. Then comes the sample informativeness score. It is basically a function. It can have different forms. So, or to make it simpler to understand, you can think of F as a feature extractor, which extracts specific features from the saliency maps. And here we look at the different feature extractors of the different functions. So first is kurtosis. So if you look at if you recall the plots that I showed before, which are these, you can see there is a distribution of the two high informative and low informative images. And then what exactly is kurtosis? It's actually a fourth order statistic. And so you have mean, you have variance, which is first order and second order. Then you have third order is skewness, and fourth order is called kurtosis. Kurtosis gives a measure of how heavy-tailed the distribution is. Or for example, high kurtosis means there are lots of heavy tails, which means there are a lot of outliers. And low kurtosis means which do not have a lot of outliers. So it's more or less a desirable thing. Then the second type of features we use are radiomics features, since we are dealing with radiological images. So there is the SPI radiomics package, using which you can extract different kinds of features. Like there is first order statistics, gray level co-occurrence matrix, which is essentially texture features. Then there is shape-based features, which would extract a convex hull of the mask and then do some analysis on this particular mask. Then the third one is what we did, what the new type of features we propose is the deep saliency features. So, well, the features by themselves are not new, because we take the saliency maps and use autoencoders for reconstructing them, and we take the latent feature vector as the deep feature. But then again, we have this self-supervised learning component. So this is what I meant by the self-supervised component. So if you recall, I mentioned previously that there is no ground truth label for which is the most informative sample, which is the least informative sample. So in order to identify that, we do a bit of self-supervised learning. So what we do is, so let's say we have a saliency map, and then we extract this feature, the latent representation of an autoencoder. Let's say in a batch we have n number of images, let's assume 32 or something. Then we cluster all the features into k informativeness clusters. So now the k is a parameter which we can set depending on the granularity of the informativeness we want. For example, if we want to rank them on a score of 1 to 10, we can choose k as 10. If we want 1 to 5, we can make 1 to 5. So obviously, the higher the k, the more granular the representation or the informativeness is. But then the downside of high k is that you have very few samples in each cluster. So for our experiments, we chose k as 10. So what we do is we do the clustering into k equal to 10. So after the clustering, so we have now 10 clusters, and each of the feature vectors in a particular cluster, I mean, like the set of feature vectors in a particular cluster, they are similar in terms of their features. But we still don't know which is highly informative and which is low informativeness. So in order to identify that, what we do is we take samples of each cluster by turn, we add them to a training set, and then we retrain our classifier, and then check what is the change of the performance. So like we take this area under the ROC curves as a measure. So we check, so whichever cluster gives the highest positive change of AUC, we said that is the most informative cluster. So then all the, so now we assign labels to each of the samples in that cluster. For example, let's say in cluster 1, which is the most informative cluster, suppose we have 4 samples. So then all these samples are now labeled as 1, which is highly informative. So then we, so we rank informativeness clusters and assign labels. So now what we do is we have this, so now our objective is that when a new sample comes in or a new saliency maps comes in, we want to directly predict whether it would go to cluster, whether it would be informativeness rank 1, 2, or 10. So in order to do that, or that informativeness label. Sorry, I missed. So can you hear me now?
Yes, sir. You can clearly hear.
Okay, I think might be some problem with the internet, so I'll just switch off the video for the
Yes, sir, yes.
duration of my presentation. Okay, great. Okay, so now what we have is we have this random forest. Now we have the feature vectors, and now we have the corresponding informativeness labels. So now we can train the random forest. So what happens is once our training set is complete, when a new image or a new saliency map comes in, we just take their feature and use the random forest to classify whether it's a high informative or not. So if it's a highly informative, then then accordingly we can ask the clinicians to annotate those particular images. So this is a TSNE plot visualization, which basically transforms the high dimensional data to a 2D low dimensional feature space for visualization. And these are the rank of the, these are the clusters, and we see that they are fairly well separated. And so what this makes us feel is that yes, the deep features that we used and the the self-supervised learning approach that we use, so those are fairly effective in identifying the most informative clusters or the most informative samples. Now, there are some classification results I want to talk about. So what we did is we tried out different kinds of classifiers. So in an active learning setup, so what happens in active learning is, so initially we start out with a small percentage of training samples, let's say 10%. So we train a classifier, and then we select the most informative samples and add them to the training set. And at each gap or interval of 10% training data, we plot the AUC values. So as you can see, there are different features or the different ways of determining informativeness. So our baseline method is a fully supervised learning method, which basically is this blue horizontal plot, which is based on like a 5-fold cross validation stuff we do, average of that. And then there are different, so then there is this orange plot for like randomly selecting samples without doing informative sample selection. And then we have, of course, this different methods like uncertainty. So our method is on this, the figure on the right hand side, which is this deep features. So which is this plot. And if you look at it carefully, you can see that using our deep features, we are able to get the best, highest performing AUC values or the classification performance. But there are some interesting things that I wanted to highlight on this from these two sets of figures, is that if you look at the informativeness or the sample selection based methods, so all of them they cross the fully supervised learning threshold or a benchmark at a very small percentage of training samples, usually between 33, starting from 30 to 33, and their final classification accuracy is always higher than the fully supervised case. So this is something we have been asked. Many reviewers have asked us why this is so. Actually, we can only conjecture what is the reason behind this. So what we feel is that because in the initial phases, the classifier is focusing on highly informative samples, it is able to it's able to block out the noisy samples, that is samples which have incorrect labels and all. So as a result, so it does better than than using only the conventional fully supervised case where you can have noisy labels as such. And many other researchers also report this same observation, and some of them say that there is a kind of teacher-student relationship where you are trying to distill the knowledge, like the labels given by the clinicians are able to distill knowledge to this new classifier. So there are different ways to look at it, but of course this would require further research, and we haven't really gone into that a lot. and probably that's something for future work. But as of now, so this particular phenomenon is observed by other researchers as well. And then again, the same, so this plot is about using image features, like taking features from the original images instead of the saliency maps. There also we see a similar trend, but the difference is that the final values using the image features are less than those obtained from the saliency maps. Like for example, if you look at deep features, its final value at 100% is less than 0.9, it's 0.88. But in the using saliency map features, it goes up to nearly 0.97. So, and the reason for that is what we can say with a fair degree of confidence is that the saliency maps actually concentrate on the most informative region because it's an attention mechanism approach. So that's why it filters out all the irrelevant information. Whereas in a original image, there are a lot of other things like neighborhood, noise, texture, and all, which is really not relevant. So as a result, the performance in fact degrades. So another interesting experiment we did is instead of taking the most informative samples, we take the least informative samples and add them to training. And what we observe is like something like this. Like initially, the change in the increase in performance is very small, like as you can see. But then after a certain threshold, it starts to increase, and because then the least informative samples in these images are actually kind of turn out to be the most informative samples in reality. So then again, a bit of comparison between GradCam and Deep Tailor method. So a top row is a highly informative image, and bottom row is the low informative image. For the high informative image, we see that the GradCam and Deep Tailor give highlight similar regions, but when it comes to the low informative images, GradCam actually doesn't do that well, and it is not restricted to this particular example. We observe it for multiple images. So that's why we made the choice to go with Deep Tailor models. But irrespective of which saliency map method you use, the active learning phenomenon still is valid for most cases. So so then some of the conclusions from this topic is that if we can definitely use saliency maps and self-supervised learning for selecting highly informative images, and results, we apply our method on public data set. Actually, the X-ray images I showed you, it is from the NIH chest X-ray database, and we also have some conducted experiments for segmentation tasks, where we identify the most informative image, then take the mask for segmentation training that we used for actually histopathology images. I didn't show the results here, but they are part of our paper. So it was accepted to IEEE transactions in medical imaging. So it's a fairly recent paper. So this is actually this is what I wanted to talk about, the sample selection. So any questions on this topic?
So in the chat box, I cannot see any question till now. But sir, I have one question here. So in the map, in the block diagram, you have shown that from the Saliency map, we are getting the clusters, and from the clusters, we are actually doing the rank informative clusters, and then we are assigning the levels. Yeah, in this slide. So sir, my question is, how are we assigning these levels? Is it manually done, or any other mechanism is there?
So this labels depends on this step. You see this step, add cluster samples to training data plus determine data you see. So what happens is so let's say we have a base model, some model at some state, and then we take all the samples from cluster 1 or some cluster and add it to the to this training data and retrain the classifier and determine the classification performance on a separate validation set. So let's say before adding the samples, let's say the AUC was 90, and after the samples we have 91. So for this particular cluster, we have so the delta AUC is 1. So then so we do this for all the for all the cluster samples. So that means we start from the model of 90, and then we rank them based on the positive change of the AUC value. So suppose one cluster gives a change of 5. From 90 it goes to 95, and that is the highest. So that means that is the rank 1 or the cluster 1 of the most informative cluster. So now all these within that cluster are assigned as label 1. Then accordingly, based on the ranking, we do this labels assignment. So this is basically this particular module.
Okay, sir. So yeah, that is why it is called self-supervised learning, right?
Exactly, yeah. Because in self-supervised, you are generating the labels. We don't because we don't have the labels, which is the most informative and which is least informative. So we do this. It is kind of a pretext task-based approach to do self-supervised learning. I mean, self-supervised learning, there are two distinct approaches. One is called pretext task, where you define certain tasks, like what happens, you can mask a particular part of the image and predict the intensity values. Or you can, then the other part is loss function based approach, where you do this contrastive learning based thing, where one sample is transformed differently, and the idea is that it should even the transformed feature should also have the same labels as the original sample. So then they are trained in a unsupervised manner, and so it gives you a lot of finally a stable and a reliable feature extract. So this is a pretext task based approach.
Okay. So, sir, actually, I am working on functional connectivity analysis of brain. So, sir, is it possible to apply this self-supervised learning like on different images for the pretext and downstream tasks?
Yes, why not? For example, if you want to have the brain, like let's say if you have the brain MRI, I'm assuming MRI or something.
Yes.
So you can mask a particular part and try to predict the intensity of that particular region. So that's a common pretest task. Other pretest task is you can add some noise to that part and try to denoise it, or what else can be done. I think those two will be fairly effective.
Okay. Okay, sir. And so my another question is, in the ideal technology, you have said that deep saliency features. So deep saliency features means the autoencoder you have used, the model automatically generating those features. So that is called actually deep saliency features.
So basically the autoencoder is this part. So the purpose of autoencoder is to reconstruct a image. So given input image, first there is this encoder which comes out to where gives a feature like a low dimensional representation, and then using the decoder part, you reconstruct the original image, and the loss function is always a mean square error, like what is the difference of the pixel intensity value. So once that is trained, this feature, this part you can take as the deep feature.
Okay.
So that is one way to do it. Or you can take, for example, if you have a pre-trained network that has been trained on saliency maps. So many papers, what they do is they take a pre-trained model and use their feature extractor. But then the pre-trained model should have been trained on images that are similar to what you are handling. So because saliency maps are not generally used for training a model, so we take use this model approach.
So, sir, how much this technique is effective in case of transfer learning or like that?
You mean autoencoders? So
autoencoder or maybe neural network, anything. If I use it in transfer learning, so you're saying that we have to use same kind of images or the data set. So in case of transfer learning, do you think that it also works similar kind of way?
Yeah, I mean, the point is we do not necessarily have to use the same kind of images, but if you use the same, like a network trained on the same kind of images, you get the best result. But many people, initially, people, what they did is they took these neural networks trained on these natural images like ImageNet. So all these popular
Yes.
like AlexNet, VGG16, even ResNet. So you get the pre-trained models that have been trained on ImageNet dataset, and they have been used effectively in for extracting features of medical images as well. But what has also been observed is that few, like, let's say if I take a ResNet that has been trained on X-ray images, use that to extract features of another set of X-ray images. I get that feature representation. I mean the why these transfer learning is used, because these medical images are not available in large numbers. At least the annotated images are not available in large numbers to train a network. So, but that was actually the state of research a few years ago, 2 or 3 years ago. But now with self-supervised learning, things have changed. Even if you, and also you can leverage a few samples, a few short, zero-shot learning and all that to get very good representation. In fact, that if you want to really explore self-supervised learning is a good thing, you can look at these contrastive learning-based approaches for self-supervised learning like SimCLR. Then there is active learning. So those give you very good feature representation.
Okay, sir. So thank you so much, sir. That's a great idea, actually. Okay, so you can continue now.
Okay. So I will continue to the next section, which is about structure preserving stain normalization of histopathology images. So okay. So in histopathology images, what is done is there is a process called staining, where the tissue slides are stained with a particular dye called hematoxylin and eosin, and because of those components, so different structures in the tissue, they are highlighted in different regions, like pink and purple, for different structures. But what happens is, even if the operating steps are standard in the sense that there is it is hematoxylin and eosin dye, but in different medical centers there will be some variation in the concentration, because it will be a different manufacturer. The concentration of the dye will be different, and the amount of dye used for staining by a particular technician will be different. So as a result, there is a color variation of different staining, like stained images. So as a result, what happens if you use a neural network trained on one set of images and try to classify another set of images, similar images but different appearance, you won't get optimal result. So that's why so what this standardization is done, it's or stain color normalization. You can, in a high level sense, you can also look at it as a domain adaptation problem, but for histopathology images, stain color normalization is a more conventional term. Then what? Currently, the state-of-the-art methods are those using GANs, especially cycle GANs, because they first try to go from domain A to domain B and then back from B to A, so makes it much more effective. But one shortcoming of cycle GANs is that they do not necessarily preserve the shape or outlines of the translated objects. So what we look at it is, we try to integrate some kind of semantic guidance from a pre-trained segmentation network, and use that to train the cycle GAN. So the idea is that using the semantic guidance from a pre-trained segmentation network will help the cycle GAN preserve the shape features of the translated image. So this is actually the whole, like the pipeline of our method. So the red and the green blocks are the two generators of the cycle GAN. So you have image A going through generator A and getting this new different image, which is of the same appearance as B. And then there is also a reverse reverse transformation across for both the ends. So this is a conventional cycle GAN framework. Now what we have done is we take an additional module, the middle module, the light brown color module. What it does is, so this is basically a pre-trained segmentation network. Now for all the three parts like generator AB, generator BA, and this this segmentation network, we use units so that it is easier to integrate features across each scale. Now what we do is from the we pass these two images across this pre-trained segmentation network, and then take the features, fuse the features at each corresponding scale with the two original generators when we are training. So what it does is it gives you the semantic information in the at the corresponding scales of the unit or the stages of the unit. And then when we use that and train our network, this is what we get. Like for example, this image in A, we are transforming it from A to this domain B. And this in column C, we get the results using our semantic guidance. But if you look at columns D and E, there is like here, the black arrows, they highlight regions where the shape of the original images is not preserved. Like there is an additional translation or a deformation, and here there is an additional artifact introduced. But by using semantic guidance from pre-trained segmentation network, we are able to do that. We are able to preserve the structural information quite effectively. And then we actually use it for some experiments, like one is classification. So what we do is we have these two different data sets called Chameleon 16 and Chameleon 17. They are coming from different medical centers. So we train our approach we train our model on this Chameleon 16, and then transform all the images of the Chameleon 17 data set. Now what we do is we transform all the images, and then finally we use those transformed images to train a classifier. So these are the different other stain normalization methods with which we compare our method. Like so our method is called SegCNNet, which is segmentation color normalization. And then we see that so this is based on a standard database, so we get the best AUC. So these are all the AUC values on the Chameleon 17 datasets. And then we also do some statistical analysis to determine how statistically different our results are from the compared methods. And we also have results for segmentation. So again, we do the transformation and train a unit for segmentation. And so this is again based on this GLASS segmentation challenge. And this is the rank 1 method. Like this particular method is ranked 1 in the challenge, and these are two other methods that have used stain normalization. The rank 1 method, they use stain normalization, but not GAN based. They use more of the classical approaches, but these 7 and 20 are more of the deep learning recent works. They're using deep learning and using GANs. And our method is over here in the first set. And again, we are getting the best results among the benchmark data, benchmark methods. Okay, so this was about the stain normalization. Any questions on this part?
Till now, sir, in the chat box, I'm not seeing any questions, sir. You may continue.
Okay, fine. We can. Fine-grained feature maps.
One participant from YouTube is asking, does the segmentation model act as the teacher and the cycle GAN student model?
No, this particular part it doesn't have to do with. Okay, so I understand what you mean. Okay, I think he's referring to this. In a way, yes, because yeah, so this is kind of giving a semantic guidance. So the segmentation network is does act as a teacher, but it's not exactly the way you understand a teacher and a student model, especially in terms of knowledge distillation. It's not exactly that way. It is I mean, you can say that the segmentation network acts as a oracle, or it gives information, semantic information, but do not confuse it as a teacher model in terms of a knowledge distillation approach. I would like to, that's what I would like to answer.
Okay, sir. He asked again, also given two lanes A and B is the process, train on A, style transfer from B to A, then test on the newly transferred set.
Sorry, I did not understand the question.
I think he's just trying to understand something. Like he's saying that also given two lanes A and B is the process, train on A, style transferred from B to A, then test on the newly transferred set.
Okay, so the experiments are something like this. So I have two data sets. So I train my model on one data set, this Chameleon 16. So then from Chameleon 17 data set has 5 different medical centers. So I fix one of the, so using this once I've already trained my model on this Chameleon 16 dataset, I transform all the images from all the 5 centers of the Chameleon 17 dataset to a common appearance space, and then use those set of transformed images to train my to evaluate my performance. And this is what all the other methods also do. They transform all the images to one particular appearance, and then they train a particular classification model. I hope this answers his question.
Yes, sir, that was clear. I hope you got your answer. If you have any question, any other question, please you may ask in the comment section. Yes, sir, you may continue. If any question comes, I will refer to you.
Okay, great. So then, so the next part is about registration of histopathology images. So again, if because of the stain normalization procedure and tissue preparation, there are some usually some elastic deformations that happen because of compression, or there is a displacement. It's not a common reference point. So what? So here we wanted to actually combine segmentation information for registration in a deep learning framework. So compared to conventional, like the classical registration approaches that use iterative optimization, although their advantage is that you don't have to have a lot of training data, but these optimization approaches, they take a lot of time. So what happens is we don't generally have that luxury of time. So deep learning methods, although the training requires data, lots of data, but in the test deployment phase, you can quickly do the registration. So, and again, registration and segmentation are interrelated. So so many works have used actually combine them together. So what we did is we had a way to, so we use self-supervised learning to generate some segmentation maps, and then fuse that map in a registration framework. So, so this diagram will actually explain it better. So let's say, so what we are doing is, if you so this the third pane, the third panel, it depicts the overall registration framework. So like we have an image pair, we get their fine-grained feature maps, pass it through a registration network to get a registration field, and use a STN to get the registered image. Now, so in order to get the segmentation maps, so what happens is, segmentation is something like, so if we have available manual segmentation maps, then it is easy, we can integrate that. But it is not, but manually annotating medical images for segmentation is very laborious. And especially if you want to do it very fine-grained, fine-grained is necessary, is more informative for histopathology images, because we have all these fine structures. But that is not actually possible. It's not, you can't expect a clinician to annotate it at such level of detail. So instead of relying on manual annotations, so we generate these fine-grained segmentation maps. So what we do is we take an image, we apply some kind of synthetic deformation using, free-form deformation, B-spline based free-form deformation, and we first we identify the different structures of interest in this particular image. So like we can use a simple watershed based segmentation to identify different structures, and then we apply some synthetic deformations to enlarge this, and then I use a self-supervised registration network to get back the original image. So where does the self-supervision comes here is that we know the what is the deformation that has been applied to this particular structure. So when we are trying to register, so we can always calculate the applied deformation and the recovered deformation. So this is where our self-supervised learning comes into the picture. So then once this registration network, self-supervised registration has been trained, it can act as a very good feature extractor as well. So then what we do is we take these input images, pass it through this network, and we get these feature maps. So now we use these feature maps to do some more clustering. So initial feature maps are generally coarse, but we use a bit of clustering, and then we get a fine-grained feature map. And then, so now we have this fine-grained feature map without having to rely on manual segmentation labels. We put it through this registration network, and we do the and now we do the registration of the actual images. So some of the results of the intermediate stages are like this. So as I said, initially we do this watershed segmentation, and then apply deformation field to get the original structure of interest. Now we don't apply it just for one structure, but we apply it on multiple structures. So I've just shown one just for a illustration purpose. And then these are the different stages of that self-supervised. Like initially we had this big image, we select a patch, and within that patch we identify one of these structures. We enlarge it. As you can see, this region has been enlarged here. And now we use the registration to get back the original structure. And then we have this, now again, we have this pre-trained network, and then we can use it as a feature extractor, and then use further clustering to get a fine-grained feature map. And now these are the examples of some fine-grained feature maps. So this is like, these are some sample images. So like this is, so if you look at the second and third image, so this is actually the image pair to be registered. So you can see there is a bit of displacement. This particular structure is not of the same size in both images, although it's the same structure, and there are some difference like translation, deformation. So now we have this fine-grained feature maps, and we can leverage that as a for the segmentation information. And now we, so again, this registration network. So this registration network is basically outputs a deformation field, and you can interpret this as a regression network. So instead of outputting the transformed image, we output a registration field and then use an STN to do the registration and to get the registered image. And then we apply it on two different data sets. So both of them public. One is called Anahyde data set, which was part of a challenge. And these are some numbers we are getting from like some figures. Like if you take this, that the I reference image and floating image will be registered to reference image. And then before registration, these are the regions of misalignment. After registration, using our method. And then after registration, if we do not include the segmentation information. So obviously it does help if we have segmentation information, because the major structures of interest are definitely aligned. And again, some numbers. So our method is here, the SRNet method. And here we are getting the lowest. Here the registration errors, lower the registration error, better is the performance. And so this was on the histopathology image, another data set. And then we have the brain image registration as well. We use this ADNI data set from which is a public data set, and compare it with voxel morph, which is a very popular brain registration approach. And then these are some numbers like DM is disymmetric which looks at alignment of the segmentation mask. HD is Hausdorff distance. Higher dice metric, better performance. Lower Hausdorff distance, better performance. So here our method is getting highest dice metric and the lowest Hausdorff distance value. So then again, in conclusion, we can say that the semi-SSL approaches are very good in feature learning the feature representations, and we can use it for different kind of applications as well. And so this concludes the registration section. So any questions?
Yes, sir. So many people were watching through our YouTube channel. So, sir, there's a question: which type of software you have used to do this method?
I have used. So this particular one was done with TensorFlow. Yes, for TensorFlow, using TensorFlow.
So actually, your voice is breaking a little bit. Will you please repeat it again?
Okay, so I use TensorFlow to design the train the network.
Okay, sir. And sir, from my side, I have a question, sir. Can we have applied this SRNet in 2D image, right? So can we use it on 3D image also?
Direct translation to 3D may not work because what happens is in 3D images, if I use so the major change will be you use 3D convolution kernels instead of 2D convolution kernels. So, but if you use 3D kernels, what you will get more information. Also looking at the neighboring slices, but then the computation load also increases. You have to have you need higher RAM to process the slides. So the alternative is you can downsize the images and do it. But if you downsize the images, then the performance measures may not be exactly, accurate. So there are trade-offs. But I believe there are some 3D registration methods as well. I don't recall right now what are the names, but maybe VoxelMorph might have a 3D version, or. But yes, that's the difference if you go directly from 2D to 3D.
Okay. Thank you, sir.
Okay, so I'll go on to the next part, which is about data augmentation or image augmentation using by learning geometric relationships between different labels. So what happens is in medical, you see, so this one I applied for medical image segmentation. You don't generally have a lot of annotated data because, as I mentioned previously, annotating segmentation mask is very laborious, and so that's why you get generally for segmentation you have maybe 50 or maximum 100 images, especially volume if it is 3D volumes that have been annotated.
So, sorry, sir. Sorry for interrupting, sir. I missed one question. Sir, there was a question. How does feature map clustering factor in making the feature map fine-grained?
Yeah, okay. So I did not go into that detail, but what happens is once you get a code's feature map, so once we get a code's feature map, we look at we start to do fine clustering based on all the. So initially we start with we'll take k as the equal to the number of pixels. So that means each pixel is assigned a unique label. Then we gradually reduce the value of k by by a weighting factor like k to, like 0.97, like kt plus 1 is 0.97 kt. So that means what we are doing is we are looking at we are gradually reducing the number of labels. So till we come to a point where there is a so then if you are familiar with clustering, so to determine the optimal k, there are some criteria used, right? Like something called Bayesian informativeness criteria. So, and if you plot the values of BIC or AIC for different k, you will see there is it's like a U-shaped curve. It will first, the criteria will reduce, it will come to a inflection point and then starts increasing. So that inflection point corresponding to that value of k is the optimal k. So here we use the same approach. It's not exactly BIC. It's a different. It's a slightly modified criterion, but the concept is the same. We change the value of k, and then we look at where the k value gives the best result. But then again, we don't make k very small because it would make it very coarse. But then to get the optimal value of k, it is usually it comes to about 0.1 or 10% of the number of pixels. So for example, if you have a 100 cross 100 image, which means there are 10,000 pixels, the 0.1 is something like 1,000. K at when k is equal to 1,000, that gives the best fine-grained feature map. So I hope did that answer your question?
Yes, sir. Yes, sir. I hope you got your answer. Thank you for asking. Yes, sir. Please continue.
Okay, so now the next part is about learning relationships. So generally what happens in data augmentation, conventional approaches, they just, they don't try to learn the geometric relationship between different labels. But that is essential, especially for medical images, because different organs have their different dependency in terms of anatomical features and all. So here, this is basically a diagram of our generated network. So if we have an image, we can do we get that segmentation mask. If we have manual masks, good, or we can do some weakly supervised segmentation, and then we transform the segmentation mask in different ways, and then we have this generator network, which is basically a unit which basically takes its transform mask and makes further changes to that, fine level or more subtle changes. And to do that, we actually look at different, in order to introduce diversity, we introduce this uncertainty sampling at different levels. We sample different images based on uncertainty. So what happens is that then we get this new mask, and then we have, so then this semi-supervised part is over here. So when we get this new mask, like which has been transformed using uncertainty sampling, we mask certain parts of that, and then we try to reconstruct that mask. So in this way, we are able to. So what we do is, let's say there are 4 labels. So 1, 2, 3, 4. We mask all the pixels corresponding to label 3, and then we try to predict that region using information of label 1 to 4. So likewise, it learns the inherent geometric relationship between different labels. And once that is done, we use that to generate synthetic images and use it for segmentation tasks. So like here, if we take a base image against which we want to compare our generated mask, so this is what we get using our proposed method. And so these 2 blue contours highlight the 2 regions which are important. So this is particularly a case of Gleason grading and from tissue microarray images. And these are some of the results we get from competing methods. Because anyway, we don't have a lot of time, so I did not put in a lot of details about the method, but these are some results. Like if we take the segmentation mask and train a unit or a unit plus, what is it? So these are the results we are getting, like original image, manual segmentation mask, and then the different segmentation outputs of competing methods. And our method is closest to the manual masks, which I didn't include the dysmetric values, but again, in terms of dysmetrics, we are getting the closest values. So this is so then the other part is about generalized zero-shot learning for classification. Here the scenario is that generalized zero-shot learning is a scenario where we have to classify seen and unseen images at test data, but during training we only have images from the seen set of data. So for that, the common approach is to generate features that would correspond to the unseen classes. So which means you have to use some kind of generative models. But then the shortcoming is that these generative models can, they can generate arbitrary features which may not be relevant. So generalized zero-shot learning is very popular in natural images, where you define class attribute vectors for different classes. So in that way you can and then you can learn a relationship between the class attribute vectors and the feature representation. So then the advantage of natural images is that you have class attribute vectors even for the so-called unseen classes. But for medical images, you can't really define class attribute vectors, because it is very difficult to have really distinct class attribute vectors, and it's also very time consuming. So in order to overcome that limitation, what I did is I used clustering to get feature representations which are analogous to the class attribute vectors. And then this is like first we have a clustering of the seen class samples. We get these centroids which corresponds to the class representation. Then we do in the second stage we do clustering of the unseen classes. So during that time we use the information from the seen classes. Like here we employ a contrastive learning and a little bit of self-supervision. In that we want to make sure that the centroids of the unseen classes is different from the centroids of the seen classes. So we enforce that using cosine similarity or the cosine loss. And then, so I forgot to mention, we have information on the total number of classes. For example, we know that there might be 3 seen classes and 2 unseen classes. So that is one level of supervision we definitely need. At least our method at this stage needs. Maybe in future we can try to overcome that. So once we have these seen and unseen centroids, we use them in a generator, and then finally we use this. So there is this generator generates a particular kind of sample, and then we want to so we use a discriminator to determine if the generated sample belongs to the seen class, because we have tables for seen class. What is the we don't have a very reliable estimate of which are the representative vectors. So then here again we use the semantic similarity between the seen and unseen centroids. So for this particular, so what we can do is we can actually specify which class, what should be the class label of the generated vector. So from the input, like the input is a noise vector, and we specify whether we want unseen class A or seen class B, and then depending on that generated feature vector, we compare it. So if the desired vector is if the desired class label if it's from unseen class, then we compare it with the centroids again using self-supervision. So what we want is the unseen samples should be very different from the seen class centroids. That means their centroid or their cosine similarity will be very low, and but it should be similar to the unseen class centroids, which means that it can have high similarity or high cosine similarity with the unseen classes. So using this, we apply it on multiple medical image data sets. Like, so this is histopathology, chameleon 17, X-ray, 2 X-ray data sets, then Kegel diabetic retinopathy, which is retinal fundus. Then there is Gleason, which is again about tissue microarray images. And we apply different kinds of feature generating strategies for this particular approach. And once we have this, so what is done is once you generate these feature vectors, so now you can train any classifier. So here we work on the feature vectors, not the original images, because previous studies have shown that it is easier to generate these new feature vectors of unseen classes than images, because images are high dimensional and it requires the network capacity has to be similarly high, and it's not easy to do that for unseen images. So that's why it is much easier to work on feature vectors. And once we have these feature vectors, we can use a softmax, train a softmax classifier to get this images. So here there are three metrics actually. The S corresponds to seen class accuracy, U corresponds to unseen class accuracy, and H is the harmonic mean between seen and unseen classes. So it basically it kind of determines the balance representation between the seen, because the seen class accuracy might be very high and unseen class accuracy might be very low. So the harmonic mean, it kind of balances there too. And so yes. So again, so finally, if we conclude about self-supervised learning, is that we said that self-supervised learning is very useful in scenarios where we don't have a lot of annotated data and we don't have we cannot ask clinicians to annotate their data. And but it has a lot of applications. You know, it can self-supervised learning can serve as a building block for feature extractor, for training a feature extractor. And as I mentioned before, there are two distinct kind of approaches. One is called pretest task, another is loss function based approaches for semi-supervised learning. Then what are the new directions in semi-supervised learning? Well, in my opinion, we can probably explore transformers, because transformers are very good at learning global relationships, but not so good at learning local relationships, which is maybe we can leverage transformers and CNNs, which can learn local relationships and try to do some kind of feature learning. Or maybe we can come up with some new kind of pretest tasks for more complex problems. So this is basically the end of my presentation. So yeah, if you have questions, I am happy to answer them. And I'm sorry for
So we have another question from Medim Secretary Srinivas. Is there any specific reason to use random forest at the last stage from the first topic? I mean,
the ideal one?
Is there any specific reason to use random forest at the last stage?
This is, I believe, the corresponds to the ideal.
Yes,
topic.
sir. From the first topic, he's asking.
No, actually, we wanted a classifier which is easy to train and which is like can handle large data sets and multiple labels. And random forest has been is fairly reliable. I believe you can also use support vector machines, because random forest actually so one advantage of random forest is it gives a probability measure, right? And in support vector machines, it's a bit complicated to get that probability measure. So we were exploring some kind of feature importance using the probability measures. So which I did not highlight in this talk, but we use the random forest. But if it is only solely for classification, support vector machines are still useful as well. That's not an issue.
So we are actually getting the information gained from the random forest, and from there we are doing that, right? So yes.
Yes, which is the importance of each feature component we can determine from that. Yeah.
Okay, I hope you got your answer. He is saying thank you. Thank you, Madam Secretary. And another question from YouTube, Abhilash Nandi is asking, given the recent uses of transformer networks in CV, I think computer vision, yes, VIT by Google, for example, DIET by FP Research, in open domain, how good do you think transformers would work in medical domain, especially in SSL part?
Right. Okay. So first thing, I haven't extensively used transformers. That is something I am starting to explore. So, but still, from my experience, what I can say is, look, what their core methodology is, they don't require this convolutional blocks. So they use this self-attention layers and attention mechanisms. As a result, they can learn the how do you say? the global relationships very well in a but advantage of convolutional CNNs is that it can learn the local relationships, local structures, relationship between local structures. So that is what we call an inductive bias. Actually, I mean, the last part of my talk was I had some slides for inductive bias based deep learning classification, where I mean, I don't know, maybe you saw the slide section heading briefly. Yeah, so in that we explored CNNs, and as an alternative, we also looked at we were looking at transformers, but you know, for medical images, so transformers have one disadvantage is that they require a lot of training data to learn this relationship, and while it is easy to obtain for natural images, for medical images it's not so easy. But I have seen some papers that have used transformers for medical image segmentation, but again they augment the data set using the conventional data augmentation like rotation, translation, scaling. So I don't know, I mean, they report good performance measures, but I don't know how good is that. Probably it might work, but there could be some innovative ways to leverage that. And coming to your second part of how we can use transformers for
medical
domain? For SSL. Actually, that's a topic I want to explore. So one idea that I have in mind is maybe leverage the advantages of CNN and transformers together. So CNNs can give us a good idea about local structure relationship, while transformers can give us a good idea about global relationships. So some way, maybe we can combine it in some way to do this. I have not cross papers using that, so I cannot comment on that convincingly. But again, that's what research is about, right? You don't know, so no one has done it, so maybe that will be. It's open field, so maybe it's something to explore. But I believe there will be very good uses of combining both, or even using transformers alone.
Okay, I hope you got your answer, Avilash. Try to do that. All the best of that. And another question from Srinivas, that what is the aim of ZSL? Distilling the knowledge from deep neural networks or interpretability?
Sorry, purpose of what?
What is the aim of ZSL? I think there's a term. So
zero shot learning.
Yes, and he's saying that distilling the knowledge from deep neural networks or interpretability.
It is more to do with, I would say, distilling maybe at a very high level, but definitely it's not interpretability, because zero shot or ZSL is zero shot learning, where you try to generate feature representations of a class you have not seen, and you use the seen classes to generate features. So in a way, it is kind of knowledge distillation. That means you are relying on certain assumptions. So especially in the field of natural images, so you have class attribute vectors. So you learn a representation of class attribute vector and feature vector of the seen classes. And now when you have unseen classes, so you take the class attribute vector of unseen classes, use the knowledge learned in the previous, like between class attribute vector and feature vector to generate this new feature. So yes, in a way it is knowledge distillation, I would say. Not exactly, I would say it is knowledge transformation in one sense. But yeah, in a high level sense, it can be a type of knowledge distillation, but it is definitely not interpretability, in my opinion.
So, sir, my question is that when we are actually selecting the features, in case of machine learning, in case of deep learning, we are automatically extracting the features. But in case of machine learning, if I want to use, then should I use as much number of feature as is available, or like we should apply some feature selection method to select the best features, optimized features, and then apply self-supervised learning?
Yeah, I think I think we should use feature selection, because in one, like when I was working as a postdoc, in one of the papers, what we did is, so we had a lot of features, and given that we tried to do an exhaustive search and try to understand what is the individual contribution of each feature. So we found that if the features are noisy, then it actually degrades your classification performance. Exactly. So in that sense, it is always good to use feature selection. So that means random forest is a very good way. Then there is XGBoost if you use classical machine learning. So definitely you can use those to do feature selection.
Okay. Thank you, sir. So I think no more question. If you have any other question, please ask. We already crossed our time. So thank you, sir, for giving your time. I think medical imaging is a very interesting topic nowadays. It's one of the richest source of information about the patient and often one of the most complex things to understand actually. So yes, exactly. There are so many open field there where you can do the research and get amazing result from it. So thank you so much, sir. Now we just want to do a short photo session. We want to take a photo with you, with all the volunteers, as it is online, so we cannot do it on offline mode. So all of the volunteers are requested to turn on your camera and be a part of it. And Shourabh, will you please take a photo for us?
Yeah, I also forgot to mention, like in case anyone has other questions, they can contact me by email.
Yes,
I'm happy to answer any of them.
Yes, this is a very short time. Sir has already spent too much time with us. So that is why if any question arises in your mind, please contact with sir, and best of luck. So Shourabh, please let me know when you are done.
I am taking it.
Yes.
Just.
Done?
1 minute, just 1 minute.
Okay.
Yeah, done.
Please everyone turn on your camera.
Yeah, I would also like to thank Aishwarya because she was coordinating all this. I mean, there was a bit of delay from my side, so yeah, apologies for that as well. But I think all is well that ends well.
Yes, exactly.
Yes, done. Thank you.
Thank you to all of the members of our team for arranging this webinar, and thanks to sir again. Sir, we have a small token of gratitude for you. So I would like to present my screen, and I hope it is visible. So thank you so much, sir. On behalf of IEEE Computer Society Student Branch Chapter, IEEE Kharagpur section, I would like to thank you for delivering this talk. And sir, whenever we will send this memento to you, as it is a online session, so we just do this much only. So thank you, sir. Thank you so much for your time, and we would like to listen more from you whenever the situation will be normal. We would like to invite you as in person in our campus. So sir, thank you so much, sir.
Thank you for this very nice memento, and I will be very happy to visit Kharagpur again after many years. I'll be happy to visit. Of course, let the situation become normal.
Exactly, sir. We all are waiting for the day when all of the situation will be normal, and we are just keeping our finger crossed. And all of the participants, hope you enjoyed this session very well, and also be safe, get vaccinated whenever possible, and let's hope for the best in future. Thank you, sir. Thank you so much for your time.
Thank you for your efforts. Bye bye.